All right, welcome back, you guys. So this is going to be a quick exercise in looking at units in a calculation. And the reason is we can use units to help us verify whether we're doing things correctly and whether our measurements are going to jive and what the units should be on the final answer that we get. So for this, I'm using Beam Deflection from Principles of Engineering. And what we have is a beam, and we're going to apply a load to it right in here in the center. Cross-sectional area is pretty basic, and I'm not going to bother going through the calculation for the area moment of inertia. We just have this number, 20.8 inches to the fourth power. The elastic modulus is given as 1,600,000 psi. PSI stands for pounds per square inch. And so I can actually rewrite that unit as pounds, and to jive with this pounds, it's going to be pounds force per square inch. So inch squared. Same thing. That is that. The length of the beam is 6 feet, and the force we are applying is going to be 225 pounds of force. So using this information, let's go through the calculation. And for this exercise, I don't need to use the numbers. Here's the formula for the maximum deflection of the beam under these conditions when the beam is supported at each end and we're applying a load right to the center of the beam. F is force, L is the length of the beam, 48 is just a coefficient, a number, E is the elastic modulus, and I is the area moment of inertia. And this is the formula we have to get the deflection of the beam. So we expect the deflection number, the deflection quantity, to be measured in some sort of units of length. That's what we hope to get. Let's check it out. I'm not going to even bother with numbers, though. I'm going to just put units in here and see what happens. And so the force was measured in pounds force, and length was measured in feet, but that's cubed. And we have a 48, so 48 has no units to it, so I'm not going to show anything here for the 48. The elastic modulus was measured in PSI, so that's pounds force per inch squared. Those are the units of elastic modulus, PSI, pounds per square inch. And area moment of inertia is in inches to the fourth power. All right. So as soon as I write this with the units, hopefully you immediately see the issue. The issue is this guy right here. Because I've got other units of length or distance that are inches, but that one's in feet. That is a problem. The units need to jive with each other. So I've got to go from feet to inches. So feet is equal to, well, yeah, it brings in a number. I've got to convert. 1 foot is 12 inches, right? And so what happens is when I go to calculate the answer, a numerical answer, I have to realize that I'm not using 6 for length. 6 feet, 6 times 12, 72. I have to use 72 inches for the length. And so to compute the answer, that's the number for L that I would use. But here I'm not actually computing the answer. Here I'm just looking at the units and how they all come out to something that's going to be good for measuring the maximum deflection, a final single unit of length, of distance. So I will change that to inches right here. For length of the beam is now measured in inches. Cool. And so, fraction within a fraction. Not very keen on that, so check this out. A little bit of math if you don't realize this. The denominator of this bottom fraction can be brought up to the top of the main fraction. And so what I have now is inches squared on top. All right. Then I have pounds force on top. And I have inches cubed on top. And what do I have left on the bottom of the main fraction? I have pounds force. And that's gone. That was moved to the top of the fraction, and then inches to the fourth power. So some interesting things are going to happen here. We're going to see some cancellation, right? So pounds force and pounds force cancels out. And so, well, look at this. So it's all inches that are left, but look at the powers. I have to reconcile all this information here. Inches squared times inches cubed is inches to the fifth power. So when you multiply with powers, you end up adding the exponents like that. On the bottom, I have inches to the fourth power. When you divide like this with exponents, you subtract. So 5 minus 4 gives you 1. So we are left with inches to the 1 power. Anything to the 1 power, we generally don't write the 1 power. We don't write the exponent. So we just have inches. That is the unit of measure of my maximum deflection. That's how the units all work out. And that's what I wanted to show you guys. Not so much the calculation involving the numbers, although remember, we've got to make sure that our units jive with each other, and that does affect the computation with numbers that you'll do. The point here was the units, and how do the units, from all of this business, all this complicated stuff, how does it all boil down to a single unit that is measuring an amount of distance or length? And it's not really a length, it's an amount of deflection. How much does that beam bend? How much does it deflect from straight line downward in the middle? That's what we're measuring. Cool, just want to share that with you guys. Thanks for watching, I'll catch you next time.